All right, so here we are yet again with a new video about the Newton's cradle experiment. Draft Science has made a response video, and as usually, he has denied and rejected all the evidence. And he has once again brought up the argument that we have to measure the arc and that we have to measure the vertical height. Now, that's true. I do not disagree with that. There is, of course, a vertical height and an arc. The pendulum is, there is an angle, right? But it's so significantly small that it's negligible, okay? Especially within my latest couple of Newton cradle experiments. However, I have done this in the past with my previous Newton's cradle experiment, which is this one with the two steel balls. I have calculated the length of the arc. I started with like right before 5 frames before collision, and then I measured the angle, and then 5 frames later, just right before collision, I measured once again the angle, and then I took the difference and I calculated the length of the arc. And guess what? It proved you wrong as well. But as usual, you also called it a crap video. So here we are once again. Let me play some of your video.
So the simple argument is that yes, there's mathematical theory that you can use to figure all this out. You know, you can use the arc, okay, the angle at which you're turned, and that'll tell you what position on this circle you're at.
So I have done that. It's right here. The video exists.
They can calculate all of this stuff, like this distance versus this distance. This is all mathematically doable, where you can detect how this height.
Oh, it's not prepomatics this time?
Okay, by doing some math. Okay, by the distance this way will tell you the height this way. And the simple argument is at the bottom of the curve, you get lots of energy this way, and you're not fighting gravity. So this is really easy motion. Okay, very
yes, I do agree with that.
To go here, a high amount of energy to go here. Any motion this way up here.
Yes, if you're going upwards, you have to fight against gravity, so it has to overcome more force. I do agree.
Has a huge component against gravity, so it's got a huge force it's fighting. So very little force being fought here, a lot of force the higher you go.
Yes, okay, that's all fine, but we are not. It doesn't really matter for the purpose of this experiment. All we want to know is its peak velocity right before collision. We're not interested when it goes upwards again. We are interested in the right before collision. A couple of frames right before collision and a couple of frames right after collision. That's what we're interested in.
Simple argument is the position from which he launches the object. The idea here for this.
We are not interested in the position of the where it is launched, the launch or the release position. We are interested in its velocity right before collision and the velocity right after collision. So why is it so important for you to know the velocity or the whole process, the whole acceleration process, starting from its release, starting from the point of release to collision? Why do you want to know every step, every point across this line?
Simple equation in terms of finding velocities is really just about this height. And the argument is this 4 times the height or is it 8 times the height? So you go 4 times higher or is it 8?
In comparison with what? 4 times higher than what?
Times higher in gravity. And then when these two things hit, does this object swing? Okay, here, okay, which would be, let's say that's would be the mark for 4 times. Well, that would be the mark for 1/2 the velocity. 1/4 the velocity, and this would be the mark for 1/2 the velocity, something like that. So this would be where it would go if it had 1/4. This is where it would go if it had 1/2. This would be 4 times the difference. This would be 8 times the difference. So this line would be 8 times smaller than this line. This line would be 4 times higher than this line. And that's how you have to really do this experiment.
So it seems like you're describing the process of acceleration. That yes, at this point it's going this fast. At this point it's going this fast. Sure, I guess that's all correct. I could do that. I could measure every point across this line and calculate its velocity. And I assume that, yeah, gravity does its job pretty well as it is acting upon this ball as the ball is falling down. All right. So it's like you want me to confirm that, yes, the acceleration process is working just fine as gravity is acting upon it. It's like you don't trust gravity. Do you want me to confirm that the acceleration process is correct? Well, in my new video, I have given you the radius of the pendulum, and you can calculate it for yourself. But of course, we are just interested in the fragment right before collision, the peak velocity, not the point of release and then accelerating. I mean, I assume that works just fine. This is something that I cannot engineer.
There's no real way to detect the absolute velocities except for averages. So you have to watch.
Of course, there's always going to be average. Yeah, there is no other way. I have to take the difference between a couple of frames, and then you have to calculate the average velocity within those couple of frames. And so the less frames you use, I guess, the more accurate your indication of velocity will be.
Thing move a whole distance. But obviously, you can't watch them move the same distance because he has the ruler in the wrong place.
Now it's in the right place.
So that won't work. Obviously, when this one's up here, it's going to be closer to the camera too, which is a real problem. So you really can't get a velocity reading that way. But regardless, you have to do this the right way, and he just insists on doing it the wrong way. And so he's just basically saying, well, look, I've measured this motion, and he's created a notion of how fast.
Well, now I have measured the vertical height. I'm going to show you. So I'm talking about right before collision, 5 frames, and then 5 frames later, right before collision. I've measured the difference in vertical height. There is none. There is no difference in vertical height, so we can ignore that.
It's going when it hit. There's no way to know how fast it's going when it's hitting because, frankly, it's going faster and faster and faster. Every little mark is going faster. So if you take an average over...
Well, let's see. I took 5 frames. I calculated it. I calculated the average velocity within those 5 frames. And then I took 3 frames, done it again, and they still came out both half the velocity.
This distance, that average will be below the actual speed, obviously, because it's going slower here and it's going faster here. So
yeah, we're talking about minute details, extremely small differences in my experiment, at least.
Almost no point taking an average over this distance because that won't tell you the actual velocity of the object.
Look, let me show you. We're talking about very small distances. So there we go. This is the point of collision. And I'm doing this 1, 2, 3, 4, 5. And that's it. This very small gap. I'm calculating the average velocity in this small gap. And then the same with 3 frames. 1, 2, 3. Even smaller. But the smaller we go, let's say 1 frame, it becomes really difficult to have a good indication of where its location is. So I'd rather pick 5 frames and 3 frames. Now, of course, if I'm going to start from here, then yes, that's a lot of difference. But 5 frames is a really small difference in displacement.
You have to get its maximum velocity, all right, and compare it to these things, or better yet, use the absolute position. So
why do you have to compare it with the point of release?
I'll tell you. So if he filmed it the other way and got these angles, what's this angle from 90 degrees?
Well, this time I'm not going to do it. It takes so incredibly much work to construct all this, to the circle and to find out and to draw everything. I might want to do it again, but not this time because there is no difference in vertical height. So let me, well,
we're on 90 degrees. And
anything else here?
Of as it swings up, what's its angle? If you got those angles, well, then there is math to do that. I don't know it. I can't give you the formula, but it exists, the formula. Or you could just do this. You could just draw the damn thing, okay, on a piece of graph paper.
All right. So let's just start with calculating the velocities. Right, let's continue with calculating the velocities. So this is right before collision. Then 5 frames before. 1, 2, 3, 4, 5. Let's first check out the difference in vertical height. .6 roughly. Yes, 8.6. And 8.6, so there is literally no difference in vertical height. So now let's check. So we can ignore that. Now let's check out the horizontal displacement. 6.2. 5.3. 6.2. 6.2. 5.3. What do we have? So the velocity is 0.18. So now it should be half the velocity, 0.09. Let's take a look. After collision. This is after collision. Print screen. Five frames later. 1, 2, 3, 4, 5. Right. The small mass ball starts over here. Hold on. Zoom in a little bit more. I think it's closer. Yeah. 6.1-ish. 6.1. And over here seems to be 5.6, 5.7, 6.1. 5.7. That would be 0.08. Or it should be, we'll take a closer look. No. Should be 5.65 to be correctly. So, oh yeah. So in the middle here. Well, roughly 5.6, 5.65. As you can see, it's very close within that range. 5.6, 5.65. So yeah, really close to half the velocity, I would say. Now the other ball. What's that? 6.4. And then we have like 6.85. Is that it? 6.4, 6.4, 6.85. Yeah, which gives us a perfectly halved velocity, 0.09. So yeah, once again, so for 5 frames, once again, it shows that they reflect with half the velocity. So now let's take 3 frames. So we go back. Right, point of collision. Once again. Then 3 frames. 1, 2, 3. That's a really small difference. All right. So again, the initial position was the 6.2, 6.2, 6.2. And then, let's see, this is kind of difficult. I guess it's over here. 5.65, 6.2, 5.65. Okay. Yeah, 6.2, 5.65, right? All right, now after collision, Start with this one. Five frames later. No, three. So 1, 2, 3. One mass ball. So 6.1. And over here we have that 5.8, 5.85, 6.1, 5.8. 0.06. So to be good, it should have been 0.55. And so you would have to change, let's say it was 0.8. Hold on, 5.85. Yeah, between 5.85, 5.8 to be have the velocity. So, and that's where it is. 5.8, 5.85. Now the other one, big mass. Initial position 6.4. 6.7 or 6.65, 6.7, 6.4. Again, 0.06. If it was 0.57, oh, we got 0.07. 6.7, 6.4. 6 points. Oh, sorry. It could be 6.7 or 6.65, right? So that's also a possibility if it was 6.65. Then it would also have 0.05. So it's between 6.7 and 6.65 in order to be have the velocity. And that's what's going on here. So even for 3 frames, we get a good indication that it reflects with half the velocity once again. So there you go. Once again, half the velocity for 5 frames and for three frames. Now go ahead and call it a crappy video once again, and say again that I have engineered this experiment. How the hell am I supposed to engineer this experiment? I've made a video. I've showed you how I put up the setup. Okay, it's right here. And I simply suspend the balls. I place them next to each other. I raise up, I raise the one mass and I drop it, and that's it. And everything else is just nature at work. I do not engineer how nature works. Or somehow do you think I have placed so secretly I have placed little motors behind the balls that can accelerate them after reflection or something like that? That's ridiculous. So take it or leave it. Of course, you will deny it and reject it.